Alright, I'll give it one more minute and then we'll start. Alright, let's get going then. So today we're going to cover return-oriented programming. Okay, so today we're going to cover return-oriented programming for binary exploitation. So our goals today are going to be understanding what return-oriented programming is and how to use ROP chains to achieve at least some arbitrary code execution. Some relevant courses at the University of Calgary are computing machinery and principles of computer security. Tools we'll be using today are GDB, Pwn tools, ROP gadget, and object dump in Python 3. So make sure you have those installed and ready to go. Uh, these are some prerequisites for this workshop. You should at least be familiar with these concepts because I'm not going to be covering them in like super detailed. I'm not going to be covering them in detail, so you should know what strings, characters, bytes, bits, ASCII, buffers, and stack and buffer overflows. You should be familiar with all that. And I have a disclaimer. There's easy ways to get the flags for some of these, well, for basically all my challenges, but the point is to learn and to understand what we're doing. So you can get the flag, but if you get the flag the easy way, you're just cheating yourself out of the knowledge. So keep that in mind. All right, so let's start with some quick review. We're going to be following the AT&T syntax, which is just the default syntax for GNU assembly. So it, it's just I think the abbreviation is GAS. And let's just start with some x86-64 instructions review. Uh, so we have move, push, pop, and ret. And I want to first start asking with if anyone remembers what these instructions do. So you can type in the chat and do that. Yeah, that's basically correct. So move is just it just pushes from sorry, it moves from source onto a destination. Push pushes from source onto the stack. Pop pops the top of the stack into a destination, and ret does a pop return address from stack and you jump there. This is some quick register review. It's not super important that you remember this in detail, but basically these registers over here are considered caller save registers, meaning that they're not necessarily saved across function calls, and they're basically just general purpose or scratch registers. And by convention, RAX is used to store a function's return value, and the register RSP is used as the stack pointer, which is a pointer to the topmost element in the stack. Uh, then we have these other registers, which are called callee save registers, meaning that they are saved across function calls, or in simple terms, they are reserved. By convention, RBP is used as the base pointer. Okay, now let's do some buffer overflow review. So if you remember your classic buffer overflow where we jump into a different function, uh, I want you guys to basically warm up and try and do the easy jump exercise in the files that I posted in announcements and workshop tools. And I have, I think, so change directory into. So I have you guys, I put an exploit.py file in there already, which has some stuff in there to get you guys started, and so uh, kind of give you guys an idea of where to start. So I want you guys to try that for like, say maybe 5 to 10 minutes. And if you remember, a buffer overflow is just you overflow all the way up into the return address, and at the return address you want to write an address where you want to jump. I'm gonna play some music now. Let me know if you guys need help or anything. Oh, the link expired. Oh, by the way, I actually wanted to cover this real quick, just to kind of clarify what number packing is. If you looked at the exploit.py file, you should see that I pack numbers with P64 parentheses. So it might be unclear what that is. So I have a number packing.py. If you run this, you can see that the number, um, you can see that 0x deadbeef. If you just print the number, just 0x deadbeef, it's going to give you this number right here. It's just going to give you a decimal number. Whereas if you pack it in P64, it's going to give you the little Indian packing of that number. And that's what you're going to write into just a normal file. And eventually that's going to give you bytes. So I'll show you what that looks like in a minute. I think I'm just going to do maybe like 2 more minutes, unless anyone needs more time. I think I'll go up to a hint right now. Unless, does anyone object to a hint? Okay, Alex. Do you guys want a hint? Um, no, I'm running them on Arch, so I have no idea why they wouldn't run on Mac OS. Hmm. I think I'm going to give you guys a hint, unless someone really doesn't want one. So I guess the first obvious hint is figure out how many bytes you need to cause a program to segfault. And then you want to jump to an instruction the program can execute, like a function call. So here's the return address. Instead of having CCCC, you want to have an address. Okay, I think I'm going to go over the solution. Unless someone objects. Hmm. Okay. I think for now I'm just going to go over the solution. So here's what the easy jump code looks like. So you have just a function, void easy jump, but I don't call it. However, we have a buffer overflow vulnerability because I use getS, and as we all know, getS doesn't check for a limit; it just overwrites the it causes a buffer overflow. So the high-level solution is you overwrite everything in the stack up to return address, and you replace the return address with the address of easy jump. And uh, there's not much to it. Here's my solution, and I'll show you guys what it looks like here. So we first map the elf, then we have some padding. So we just figure out how much padding we need. Then the address of the gadget, that's just for a placeholder, just an example. We're going to get to that later. Then we find the address of easy jump. We can do that by using the E from the map. E is equal to elf. We can use that and find in the symbol table, we can find the address of easy jump. And then finally, we just do payload is equal to padding plus easy jump. and then we write that payload into a file called in. So if we look at in is just my payload. So it's just a bunch of A's, and then these things are actually the bytes of the address. So it looks like that because it's basically bytes. It can't really print those bytes. So let's look at it in GDB, what it looks like. Up, easy jump. So if we break main, run it, examine 10 instructions from the program counter. So here we can see that the return instruction happens at this address. So let's go, actually, sorry, my bad. I have to run it with our payload. So run with the hat and then in, yes, and then examine 10 instructions again. So this is this is the address we want to pay attention to, because if we wrote our payload correctly, then we will be jumping into easy jump instead of exiting the program. So we continue. Okay, so we are now at this address. So if we examine 10 instructions for the program counter, we can see there's nothing unusual, but then we do another instruction and we are now in easy jump. So if we examine another 10 instructions, we can see that we are now in easy jump and that we can get our flag. So let's run the payload cat in easy jump. Oops, no. Cat in pipe into. There we go. And there we go. There's the flag. Oops. So if you remember the code, right, I don't call this function. Instead, I am using return-oriented programming to jump there. And we can get it to execute. Is everyone clear on that? Any questions? No? All right. Let's move on then. So let's get a little bit more complicated. What is actually return-oriented programming? ROP is a technique used to gain control of the call stack in order to hijack program control flow and bypass mechanisms, uh, bypass defense mechanisms like stack not executable and ASLR. So how are we supposed to do this? Well, I'm glad you asked. No, even though I can't hear anyone. We use these things called gadgets. Now, ASMR. So gadgets. To hijack control flow, we want to execute specific machine instruction sequences that already exist in the executable part of the program. These are called gadgets. Gadgets will always end with a return instruction so you can chain it and and go to another gadget. A really useful sequence is pop RDI ret. So if you remember, pop it pushes from the stack, or sorry, pops something from the top of the stack into the destination, and ret just lets us jump somewhere. Is there any questions on this? Nope. Okay, I will move on. So for exercise 1, I want you guys to just use this thing called ROP gadget. And ROP gadget is used to find where these sequences are in the actual binary, the address of where the sequence starts. So if you go change directory x1, so if you go there, then you can just use ROP gadget on the find gadget binary. So yeah, just give that a try. And also you can try it on other binaries in your system, not just the one that I have. You should be able to find plenty of gadgets. It's almost impossible not to, I think. So I'll just give you like 5 minutes to do that. There's also a really easy flag in this binary. Okay, I think I'm going to show you how to do this. It shouldn't be complicated at all. This is just running a command basically. So if I do ROP gadget dash dash binary on, it's called find gadget, and you can also use grep instead of the dash dash only. Grep might be a little bit easier. So if we grep pop, then we can actually find the address of a gadget here. So here's pop RDI return, and here's the address of the gadget. All right, is that clear? Does anyone have any questions on what a gadget is? Like, is anyone confused on that? All right, I will move on then. Okay, so what makes per or pop RDI ret special? Well, the first instruction, pop, lets us basically pop a value onto the top of the stack. So when overflowing a buffer, we can place values at the top of the stack. And if you remember, pop D pops the top of the stack into a destination. So if we have a buffer overflow, we can replace the return address with the address of this gadget right here. So we can replace the return address with something like this. And then we can give it a value that we want to pop into whatever, right? So we can actually give almost like a function argument, right? We can overwrite this whatever is right here and pop that into a destination. So the destination in this case would be RDI. So if you remember from the assembly review we just did, RDI is I think I said it was Kali, like a scratch register or general purpose register. And if you run object dump on the file 1arg, you can get the assembly of main, and you can see what a function call actually looks like. So let's do that. Change directory to. So here we have 1args, So if we look at the function, or sorry, the C program, it's just a normal call. There's no special code in here, right? So we have main, and main just calls normal call. Nothing special. So if we do the object dump of one args, let's pipe it into dump. All right, so now here we can search for dead beef. Here it is. So here's main, and as we can see here, before the call to normal call is made, this is normal call, right? This is when the call is made. Right before the call is made, we are moving the argument dead beef into register EDI. And EDI is just the 32-bit version of RDI. So for our purposes, there's really not a big of a difference. It's more or less the same, although that's not fully true. But like I said, for our purposes, it doesn't really matter. But it moves the argument deadbeef into EDI, which is basically RDI for us, right? So here's the move deadbeef into EDI, call normal call, and that's how you place, that's how an argument is given to a function call, right? So that's why pop RDI portion of the gadget is very important. Now for the ret, when taking control of a program, of the program control flow, we want to use the stack pointer as almost of a makeshift program counter with the help of the return. Uh, if you remember, a program counter basically just points to which instruction we are currently looking at. So if we do gdb break main run, so if we examine 10 instructions from the program counter, the program counter is just pointing which instruction we're at. It just tells you where we are in the program. So we are using ret and sorry, we're using the stack pointer as a makeshift program counter by using ret and telling the program where to jump. So the order of a pop RDI return would be the address of the gadget, which we just did, and then a value we want to pop, and then the address we want to jump to after. So I don't know if you understand where I'm getting to this, but what we want to do basically is have an address here, give the give a function argument. Maybe the function we're trying to jump to needs an argument, and if you jump there without the argument, it's just going to give you an error. And then after we give it that argument, we can then successfully jump into that function. So that's the basic gist of it. ROP gadget is just going to give us the exact address of where the gadget sequence starts. So this is the high level idea. And now I'm going to get you guys to try and implement this high level idea in exercise 2. So for exercise 2, I want you guys to analyze the obstacle jump 0 binary and try to jump into the function containing a flag. Also, don't forget to pack your numbers to strings using P64 and Pwn tools. Okay. If anyone has any questions, feel free to ask. I'm gonna put some music. Keeps losing it. Yes, this is going to be uploaded later. Uh, So I'm gonna give you guys maybe like 3 more minutes, and then maybe I'll try to get you guys to work together in breakout rooms if you're feeling stuck or if you're not sure what to do, then you can guys try to help each other out. Okay, yeah, we can do 5 minutes then. Yep. Okay, so I'm thinking maybe a hint and then breakout rooms, or I'm not sure. Do you guys want a hint and then going into breakout rooms? So, so do you guys just want to try going into breakout rooms to solve this then? Okay, go join Alex, guys. No one's going to join Alex? Okay, there we go. We got some people going. I would suggest you try making your own breakout room or maybe going into Alex's breakout room just so you can move forward a little bit at least. So you're not stuck doing nothing if you're a bit stuck, I guess. If you're really adamant about working it on your own, let me know if you want a hint. And then there were four, or five technically. No. Jeremy, Josh, do you guys need a hint? Oh, give me a second, I can't hear you. Sorry, what was that? No? Oh, okay. Jeremy, I think you should be good, right? If you're speaking, I can't hear you, but I'll take that as a yes, you're good. Yeah. Oh, okay. Well, I mean, I'm asking if anyone has any questions or anything, but okay. So is there anything that's unclear? Hmm. Okay. Hmm. Right. Well, that's like I was when I tested the workshop, they I was told kind of like something similar that people might not know how to work Pwn tools for this, which is why I gave everyone I had the exploit.py included in there. In there you already have like a base and that's pretty much all you really need. So I guess I don't know if they're not looking at exploit.py, but yeah, I'm not sure like what I need to redo. I mean, like if you're specific, I don't mind. It's just that I need some feedback. I'm just gonna show some hints, I guess, at this point. I'm gonna go hop in the breakout room for a bit. See how everyone's doing there. So, how is everyone doing? Oh, that's all right. Oh no. Uh, mm-hmm. Okay, the error you're getting is because you haven't installed pathlib. Oh, you did? Oh, that's why. Mm-hmm. Okay, what error are you getting? Oh, right, I forgot your screen sharing. All right, let's see. So if you run, okay, you're getting. Oh, that's because you're writing byte. You're not writing bytes. You're trying to write a string. You're using path dot. You're trying the payload you have. Go into your exploit.py. Okay, let me see. You have. Oh, I see. So the padding should have a B in front of it to signal that it's bytes. No, not there. Like before the before that. Yeah, so there we go. Yeah, write a B there. There we go. Now, wait, why did you change it to 4A's? No, no, no. No, no, no. No, you just keep you're just telling it to read this string as bytes. That's it. Yeah. Okay, now. Oh, also you need to pack your binary dot symbols obstacle jump 0. You need to pack it to 64. So you know what you did with num underscore exa? You got to do the same thing with binary dot symbols. Yeah, so you have to enclose it with p64. Yep, there we go. Now it can write bytes directly onto the text file. And then you, yes. So what is dead beef? Yes, but what is dead beef though? Like what is 0x dead beef? Right? It's hex, it's a number. So what do you got to do with that number? Yes, it does it for you. So here, maybe watch my screen real quick so I can go over this again. Yes. All right. Yeah, that worked. Yeah, that worked. That's fine. Now you can just do cat in dash dot pipe it into dot forward slash obstacle jump and enter. Enter. There we go. Okay. I'm gonna go back to the stream chat and I'm gonna try to go over this solution slowly. Is that good? Alright, I'll try that. Alright, let's try going into the solution. So, this is the high level solution. These are basically the steps you want to go through to get the flag. First, you want to find out which function contains a flag. You can do this with a decompiler like object dump, redare. Is that how you say it? Redare or Ghidra, something like that. Then you want to determine the argument that the function needs, which you can also do through a decompiler. Then you want to get the address of that function, then get the address of a pop RDI return gadget. Then you want to find minimum bytes needed to segfault the program. And then you want to build your stack similar to this picture. So the address of the pop RDI return gadget, then a value we want to pop, so like a function argument, and then an address to jump to, so like the function we're trying to jump to. All right, let's go over the solution in my solution. So here's my solution. First, we map the L file. Mapping just lets us do some easy stuff with it, like getting the symbol table. Basically, just lets us find things easily. Um, then we figure out the padding. So the padding is just 16 A's. Oh, what the hell? Oh, give me a second. Oops. How do I show my scopes? Oops. Alright, there we go. Alright, I think now it should be fine. Is that good? Can you see my screen? Alright, I'm sorry. Okay, so first we have the padding, which is just uh, the letter A, but we want to give it the B here. The B is just so that we tell Python to look at this letter as a byte, and then we just multiply by 16. Then we have the pop RDI gadget address. So if you remember, ROP gadget dash dash binary on obstacle jump 0 grep pop. There it is. See, it's this address right here. It's the same address. Now, we want to pack it to 64. What this does is that if you look at the files to download folder, python number packing.py, this is what packing it to 64 does. So it just gives you a byte string that's in Little Indian. So here you can see dead beef. So this is DE, AD, BE, EF. So that's just dead beef in Little Indian. And this is just the decimal of dead beef. So this is what P64 does. It lets you write actual bytes to a text file. So then we do the same thing with the actual argument, 0x dead beef. And finally, we find the address of obstacle jump 0. And we also pack that to 64. Then it's just a matter of basically doing this high level solution, building your own stack like this. Padding, then the pop RDI, the argument, and the obstacle jump 0. Then finally we just use path to write the bytes to payload. So if we look at in, again, here's what in looks like. It's just a bunch of A's, and these are the actual bytes. So, give me a second. So this address right here, so here's the padding, right? First we have the padding. This is just the padding. Then we have pop RDI, but we wrote actual bytes here on this text file. See, these are like actual bytes. I don't know where pop RDI starts and ends. Well, I'm guessing it starts here, but I don't know where it ends. But the point is that these are actual bytes that you're writing to this text file. And that's what P64 does for you, which makes it really easy. Now, if we run the payload, actually not on, no, this one, yeah. Then we can jump into that function. So let's look at it in GDB. So break main and run with the payload in. So if we examine 10 instructions from the program counter, we can see that the return instruction is going to be at this address right here. So it's going to, like that's where we want to pay attention, because if we did it correctly, we should jump into obstacle jump. So if we do ni at 92, so we're at 91, 92, so we're at the return instruction. Now if we did it correctly, we should go into our pop RDI gadget. So we're somewhere in like libc now, as you can see. But if we look at the instructions, we're actually at our gadget. There it is. So now, another way to check this, to continue checking if we're doing things correctly, is to check the registers. So if we do info R for registers, we can look at RDI. So we're going to be popping a value into RDI. So right now RDI has what looks like an address. And if we do next instruction, we just executed pop RDI. So let's see what it actually has now. Pop RDI. So now look at that. It has dead beef. And the base pointer has our padding actually over here. But the important part is that dead beef has our argument 0x dead beef. So if we continue, let's see where we were. Now we're at a second return. And this return should take us to obstacle jump. So if we examine 10 instructions again, then we are now in obstacle jump. And obstacle jump is going to compare dead beef and give us a flag. So if we continue, we're going to call put as, examine 10 instructions, and yeah, I mean once you're in obstacle jump, it's basically, there's nothing really else to explain. It'll segfault because after, when it reaches this return, it won't really know where to go because you didn't give it another instruction. So that's why it segfaults. Was that clear? Or does anyone need me to re-explain? All right, I will. All right, sure, no problem. Okay. I mean, here's the drawing of the stack. So this is like the high level, right? So buffer, address to the gadget, value you want to pop, and an address to jump to. So this is the obstacle jump zero code. And yeah, it's nothing special. So here's when we're comparing 0x dead beef to the argument x. And now, yeah, this is just the solution we just went over. But yeah, we use ROP gadget, then we can use a decompiler to find dead beef, and then we can put it all together into the solution, which I just covered. But it doesn't end there. You can keep chaining gadgets to basically get some combos. And more advanced ROP attacks actually involve returning it to the C library to string a sequence that can spawn a shell. Okay, so we have covered so far how to find gadgets, how to set up an overflow of the stack to execute instructions we want, and how to put it together to deliver a payload. So for this next exercise, you basically need to find a second gadget to successfully jump into the function containing a flag. So this is going to be exercise 3, and I want you guys to try to analyze the obstacle jump 1 binary and jump into the function containing a flag. So I'm going to start you guys off with this hint right off because I think it'll be pretty helpful. So if you remember earlier in the workshop, we saw what a one argument function call looked like. Okay, so let's look at what two arguments look like. Flow, second. Oops. So, uh, if we go into function call.c, so here's what two arguments look like. We have a normal call with two arguments, and they are passed, and we have hello world. So let's look at the dump. So object dump dash d of two args, pipe it into dump. So if we look at the dump, let's look for normal call. So here's normal call. So can you guys tell me what the arguments or like what registers are being loaded before this call? You can type it in the chat. What registers are being loaded before calling normal call? No, not RSB. I mean like the registers. So here's the call to normal call, right? And there's two instructions right above it. Yes, EDI and ESI. Those are the two registers that are being used. So now that you know which registers are being used, you need to find gadgets that will let you load values into those registers. So uh, that's where you guys can start for this exercise. Let me know if you guys need any help or if you guys have any questions. Otherwise, you can hop into what's it called? You can hop into a breakout room. How is everyone doing? Do you guys need a hint or something? How is everyone doing? Do you guys feel like you need maybe a list of steps to sort of like set you on track? No? Alrighty then. Okay, I'm gonna go over just a hint of how how to go about doing this. Just a list of things or like steps you need to do in order to get the flag. Maybe you can see where you might be stuck, or maybe you don't know what to do after you've done something, so this might help. Sorry, I just realized I wasn't talking. Uh, so here's the obstacle jump one code, and it's again nothing special. We're just comparing two arguments, 0x deadbeef and 0x1337. Uh, it's not, yeah, it's a pretty simple code. All right, so let's go through the solution. What does the flag function look like, first of all? We can figure that out using object dump. So let's do that. So Python, or sorry, object dump dash D, obstacle jump, pipe into dump. Let's look at the dump. All right, so let's go to main. So here is main, and we can see that it's calling obstacle jump somewhere. Sorry, no, it's not going to call it. Sorry, here's obstacle jump. Obstacle jump 1. So now we know the name of the function, and we can see that it's comparing it to deadbeef, as well as, where's the other argument? It's comparing it to 0x1337. We know this because we can see this compare instruction right here. So CMPL, I think, is for compare long, which is just comparing two numbers, right? So we know the arguments we need, and we also know the name of the function. So now we can, I'm actually going to write this as we go, so that you guys can have a bit of an idea of the process. Alright, so we know the name of the function, so let's write that down. Obstacle jump 1. And then we need to pack it to 64, so don't forget about that. Then we need to pack it to 64. And we also know the arguments it needs, so let's write that down. So arg1 is equal to pack to 64 0x deadbeef, and then arg2 is equal to p64 of 0x1337. Alright, so we have these three things already. So we have these three things so far. Okay, let's continue. So now we need to figure out which registers it is using. So it's moving 0x1337 into ESI. So maybe let's mark that. So goes into ESI, and this one will go into EDI. So here we can see deadbeef is going into EDI. So let's write that down. Goes into EDI. Alright, is everything clear so far? Otherwise, I'm gonna move on. Alright. Now we know that ESI and EDI is used. So that means that we need gadgets that are going to pop values into those registers. So now we use ROP gadget. So let's do right quit, ROP gadget, dash dash binary, obstacle jump 1, and let's grep for pop. So if we look at our exploit, remember we need EDI and ESI, which for our purposes we can use RDI and RSI, the 64-bit versions of those registers. So here we have pop RDI at this address, and we also have pop RSI at this address. So let's copy paste those via, let's go into exploit.py, And let's put those here. And then we can pack these numbers. So let's continue our exploit. So now we have a pop RDI gadget, which is equal to P64. Oops. We have a pop RDI gadget, which goes P64, and then paste. And then we have pop RSI gadget, which is 401, 201, so we just need to change the last number. And we don't actually need all these zeros. All right, so we've got, so far, we have the arguments, arg1 deadbeef, arg2 0x1 through 37, and we have the name of the function, and finally we have our gadget addresses. Now don't forget that we have an extra instruction in here actually, pop R15. So we're gonna come back to that later. All right, now we've got basically everything we need to start building our own stack, our makeshift stack. How do we build it in order to jump into the function successfully instead of completely breaking the program? Let's see how we do that. So the high-level solution is address of pop RDI gadget first, because actually, well, it doesn't have to be first. It honestly, the order, like which gadget you set up first doesn't really matter as long as you set it up properly, right? But first we want to put the gadget, sorry, the address of a gadget, such as pop RDI, and then the value. So let's go and do that. Let's start writing our payload. So our payload is going to be our padding, which again is going to be 16 A's. Just trust me on that. I already know that. All right. So our padding is going to be padding plus, we're going to put address of pop RDI gadget. So let's do pop RDI plus value of dead beef. So let's put that arg1 plus /. All right. Then we set up the address of pop RSI gadget so that after we pop 0x deadbeef into RDI, we can jump into pop RSI, right? So we have our padding, we have pop RDI, and then we go into then we pop argument 1 into RDI, but then we have another return, so we can jump somewhere again, right? Now instead of jumping into the function, let's try jumping into pop RSI. Pop RSI. There we go, that's done. All right, then we want to load value 1337 into register RSI. So let's try that. Arg2 plus and then /. All right, and then we have an extra instruction here, so we need to give it some sort of dummy value. It doesn't matter what it is. We just need to give it something in order to so that the program doesn't segfault. So let's just give it 0x deadbeef because it doesn't matter. Actually, give it 1, 2, 3, 4 plus /. Actually, we gotta pack this. So that's just a dummy value for pop R15. Okay, then we give it the address of obstacle jump. So obstacle jump 1. And that's what our final solution should look like. And indeed, that's basically what we have. So now we write that, and then we write it to in. So Python exploit.py. Oops, looks like we didn't give it the correct file name. Oops. Obstacle jump 1. Ah, yeah, you gotta watch out for the dummy value. So you have to make sure to give the value, the extra instruction something, otherwise it's going to do stuff you don't know. So if we do Python exploit.py, all right. So if we look at in, then it looks like it wrote our payload correctly. Yeah, it just ends up segfaulting. So it looks like it wrote our payload correctly. So let's see if this actually works. And there's our flag. All right, now let's actually look at what's happening in the program on GDB. So if we run GDB obstacle jump 1, break main, run with payload in, let's examine 10 instructions from the program counter. All right, so we want to pay attention when it goes into address 401196 because that's when the return instruction is. So let's go up to 196, 95, 96. All right, so we are at the return instruction. So let's do one more NI. So we're in somewhere in libc again, and this is an executable part in the program, and we can use poprdi return. So let's look at our registers before the poprdi. So poprdi right now is like some address. We can see our overflow at the base pointer. So let's do ni info registers. Then we can see deadbeef is successfully written into RDI. All right, let's do next instruction. Actually, let's see where we're at again. Okay, we're at the next return. So that means we should be at, we should go and jump into our next gadget now. So if we examine, there it is, pop RSI, pop R15, and return Q. All right, so if we do info registers, RSI right now is 4056B1. I have no idea what that is, but we're going to overwrite it. And RSI now has 0x1337. Now we're going to overwrite pop R15. So this is the only tricky part about this challenge, is that we need to make sure to give pop R15 a valid argument, otherwise it'll just segfault. So if we do ni, R15 before is just 0, after it's going to be 1, 2, 3, 4. So the value that we gave it. And next, if we have next we have our return instruction. This is going to be our final return, and we should be able to jump into obstacle jump 1, and we do, and we just get our flag, and that's it. All right, final solution, we already covered that. And finally, I guess this is just the conclusion. If you want something harder to try in terms of return-oriented programming, you can try what's called a return to libc attack. These challenges are a little bit harder though, because it requires a deeper understanding of how ELF files are structured and how to compute offsets from libc and into the ELF file. But this is how you, like return to libc attacks is how you defeat defense mechanisms like ASLR and even canaries. And that's it for this workshop. I hope you learned something and have a good night. Unless you have any questions. Any questions? No? Alright. Yeah. All right. I think that's everything then, unless, like I said, there's any questions. Mm, all right. Have a good night then. Yeah, just type your questions in the chat. We can see them later and answer them later if you want. All right. Have a good night, guys.